Let us go to the another concept, that is just opposition. So what is the just opposition process? Here, after observing some spectral studies and experimental analysis, some compounds, even though they are actual anti-aromatic, but they are showing more stability and also showing the properties of aromatic compounds. This is why, because of the concept under just opposition. Let us see some examples. Aromaticity is strongly opposing the nature of anti-aromaticity. In this compound, it is a 4-membered ring, anti-aromatic compound, because it has 4 electrons. If there is a 4 electrons, then it comes under the 4n pi electron rule, where n equal to 1. In these compounds, when the compound is inserting in these rings, the number of pi bonds, 1, 2, 3, 4, 5, 6. So there are 6 pi bonds. 6 pi bonds means total 12 pi electrons. Any compound have 12 electrons, then we can say it is an anti-aromatic compound. But the experimental studies showing that it is an aromatic compound. Why? There is a strong possibility of conjugation of pi electrons among the ring. So if you observe in this structure, this compound is showing almost 1, 2, 3, 4 resonance structures. 4 resonance structures are possible in this case. What is the resonance structure? Resonance structure is nothing but the movement of pi electrons among all the carbon atoms. If you look at this, there is a resonance, there is a movement of pi electrons. So there is a cloud. The cloud is moving, there is a delocalization of electrons, conjugation of pi electrons. So we can also write this structure like this. So here dotted lines are, so there is a delocalization of pi electrons among all the carbon atoms. So due to the resonance structures, so there is a huge possibility of conjugation. So even though there is an anti-aromatic structure, due to the property of these resonance structures, so even though it's showing a 4n pi electron rule according to number of pi electrons, but so you have to look at, is there any possibility of movement of pi electrons, or is there any delocalization of pi electrons is possible? So first you look at that. So after finding all the facts, you can say that it is an aromatic compound. So that is called just opposition. So aromatic property is opposing strongly. Here the anti-aromatic property is suppressing complete by the showing of resonance structures. Like this, there are some more compounds. So here look at this compound. So in this compound also, so here in this ring and in this ring, the pi electrons are moving among all the carbon atoms. So here and here and here. So it is also showing almost 7 resonance structures. So it's compressing the anti-aromatic property and finally showing aromatic property. Due to the delocalization of pi electrons or due to the movement of pi electrons, so what will happen? The main thing is it completely decreases the energy of the ring. Okay, in turn it will increase the stability of the compound. So we know that aromatic compounds are more stable. Here also, in this compound also, same. There are 4 rings. So among these 4 rings, so there is a delocalization of pi electrons in all the rings. So it also showing almost more than 7 resonance structures. So this one is also aromatic compound. Let us go to the another concept, polycyclic conjugation. Polycyclic conjugation is nothing but, so there is many rings, so they are attached to one another. So if you look at this ring, this compound, so you count the number of pi electrons. So here simply you count 1, 2, 3, 4, 5, 6, 7, 8. There are 8 pi bonds, means 16 pi electrons. Experimentally, it's showing the aromatic property. Okay, so theoretically, so we can say it is an anti-aromatic, but it is not an anti-aromatic compound. It is showing the aromatic property and also it exhibits the delocalization and also the stability of the compound. So to explain this nature, so there is a person, okay, he is Kreiger. So he derived a method to calculate aromaticity of the polycyclic compounds. So let us go to the concept. So here, what is the Crags rule? It is Craig's rule. When the aromaticity cannot explain by the Huckel's rule, violation of the Huckel's rule, then that aromaticity is explained by the Craig's. So this rule is called Craig's rules. So let us see some examples. So what are the main rules of the Kreiger? So the rule number 1 is, so we should draw minimum 2 calculus structures first to in a ring. Take benzene. So you can write the resonance structure 2 kinds. So like this and like this. So these 2 resonance structures are the movement of pi electrons among in the ring. These 2 resonance structures are called calculus structure. So we should write minimum 2 calculus structures. So if we to explain the aromaticity of any compound, then there are some rules according to the calculi. The first rule is we should draw minimum 2 calculus structures along the C2 rotation. So what is C2 rotation? C2 rotation means it is an axis of symmetry. So if you rotate this compound in a 180 degrees, interconvertible into another structure. If it comes by the 180 degrees rotation, then that axis of symmetry is called C2 axis. Minimum you should draw 2 calculus structures. And the next rule is C2 axis must be minimum 2 carbon atoms. So you should pass the C2 axis minimum 2 carbon atoms. Okay, that is another rule. And next one is give labeling alternatively. Alpha, beta, alternatively. So how? Here alpha, beta, alpha, beta, alpha, beta. So you should give the labeling alpha, beta alternatively. So if F plus G is even, then it is aromatic. If F plus G is odd, then it is non-aromatic. So what is F? What is G? F is number of pairs exchangeable and unexchangeable in C2 rotation. G is simply unexchangeable spin labels. So that is G. Okay, what is F? F is if we give a rotation, then if there is interchangeable pairs or unexchangeable pairs, exchangeable pairs or unexchangeable pairs. So those pairs are all come under the figure F. So what is G? So G is strongly denoting only unexchangeable pairs, that is with opposite labels. So if there is opposite labels are exchangeable, then it is denoted by the number G. I will show some examples, then definitely you can understand.
Thank you for watching this video. In the next session, I will explain you a very important examples under the Craig's rule. Thank you. Peace out. Don't forget to subscribe our channel Live Chemistry.